Okay, what we're now going to do, we're going to solve the exact same example problem that we just solved. However, now what we're going to do, we're going to use the Heisler charts in order to come up with the solution. So I'll begin by, just like we did last time, writing out what we know and what we're looking for. We're dealing with that fused quartz sphere that is going through a changing convective environment, and we're looking at transient conduction analysis. Okay, so there's our problem statement, fused quartz sphere. We're given the thermal diffusivity, thermal conductivity. We're told the diameter is 2.5 centimeters. We can get the radius from that. Initially, it's at 25 degrees C, and then it's placed in a convective environment, hot convective environment, so it's going to be increasing in temperature, the convective environment, 200 degrees C and H of 110. And we're told to calculate two things. One is the temperature at the center line after 4 minutes, and then the temperature at a radial location of 6.4 millimeters after 4 minutes. So let's begin by drawing out a schematic for what this looks like. Okay, so our radial location R, and this is being exposed to a convective environment. Okay, so analysis for this, we're going to use the Heisler charts, and we'll start with part 1, which we're looking for the temperature at radial location R equals 0 and 240 seconds. And so in order to do this, in using the Heisler charts, we're going to begin with the one that gives us the centerline temperature. And for that, we need to evaluate the x-axis value, which is just the Fourier number. And for that, we get 1.459. And the curve that we read is, I believe I said it was 1 over the bio number, so K over HR naught. Okay, so those are the two values. Once we have them, then what we can do is we can go to our Heisler chart. So let's take a look at the Heisler chart. And here we are, very, very busy chart, a lot of stuff going on, but it's not as bad as it might immediately look when you first look at it. What we have here are our curves K over HR naught. So we have to find the appropriate curve, and we're dealing with 1.106. And so looking, there is 1 and there's 1.2, so we're halfway between those two. And then what about the Fourier number? Where are we with the Fourier number? We had 1.459, so there's 1.5, so there's 1, 1.1, 0.2. Oh, what are the increments of this? 1. So I would say 1.459, it's probably somewhere right in about here. So what I'm going to do, I'm going to sketch up, and that's up here somewhere, and we're between those two curves. So coming across, I would estimate that we're probably somewhere right around 0.05. So let's take that as being our value, and we'll work with it. Let's go back. So that gave us the y-axis value, and that is theta naught over theta I. And from that, we can go ahead and calculate T naught, because that's what we're looking for. We want to know the centerline temperature. And what do we get? We get 191.3 degrees C. And when we did this using the approximate solution from the last segment, there we calculated 192.1 degrees C. So you can see we're pretty close. We're a little bit lower with the Heisler chart than we were using the approximate analysis. But that gives us the result for the centerline temperature after 4 minutes. Let's move on now. So That was our Heisler chart. What we're now going to do, we want to find the temperature at a location off the center line. And so that was part 2. And so for this, what we're going to be doing is we're going to be reading off of a curve, r divided by r naught, which that is 0.512. And the x-axis on this curve is 1 over the bio number, 1.106. And those were that was the curve that we were reading in the previous graph when we were looking at the Heisler chart for the centerline temperature. Okay, so with that, now we go to our graph and we take those two. So this is the graph for what happens spatially. You can see on the left we have theta over theta naught. On the bottom we have 1 over the bio. So we were looking at 1 over a bio number of 1.1. So there's 1, there's 2, 1.1. I don't know, it's probably someplace right in there. You can see when you're using the charts, you're doing a little bit of guessing. Bit of a guesstimate for this. And then 0.5, well, we don't have a curve, a radial location. These are the radial location curves. We don't have any one at 0.512. We have a 0.4 and a 0.6. What I'm going to do, I'm going to go in the midpoint between those two. So we're probably someplace right in there. That's probably closer to the bottom, which it should be because we're at 0.512. So with that, we then say that that's probably the location. We come over. We're a little bit above 0.9, so let me guess this to be 0.92. And with that, we'll go back, and assuming that the y-axis, which is theta over theta naught, assuming that that is equal to 0.92, we can then plug in all the values. And again, here what we're after that temperature because that will be at the radial location at 4 minutes. And notice what we need here. We need T naught, and that's pulled from the solution from the previous part. And so that's why you'll probably recognize that number there. And then we multiply that by 0.92, and when we do that, we get T 192 degrees C. So that is the result that we get. And let's compare. When we did the previous example using the approximate technique, we got 192.8 degrees C. So slightly higher than what we're getting now, but that's consistent with what we just saw. Let's see, where was it? Here, the approximate technique was slightly higher than what we got from the Heisler charts for the centerline temperature. And so here we're finding the exact same trends. So anyways, those results are pretty close. You can see the Heisler chart is relatively quick. I didn't use a ruler. Where did my Heisler chart go? There we go. I didn't use a ruler here. And if you had used a ruler, it would be a little bit more accurate for either the centerline temperature or the spatial temperature. But when we compare the results, really not too bad. So anyways, that gives you an example of transient conduction analysis with convective environments for a sphere, one of the 3 different shapes that we can look at. And that is covering everything that we're going to look at with transient analysis and heat transfer.